Okay, so this is the what we did last time is we plot, we find the amplitude ratio x k over f naught versus the omega over omega n and zeta, and there are two parameters affecting the amplitude ratio and the phase. And then we discuss the three regions that omega over omega n is less than 1 and omega over omega n equal to 1 and omega over omega n greater than 1. And if omega over omega n very much less than 1, the phase will be almost 0. And if omega over omega n is very much greater than 1, the phase will be almost 180, or it is approaching 180. The effect of damping is obvious at resonance. Okay, so that it has no effect on the regions of omega over omega n close to 0 or very much greater than 1. The effect of damping is near resonance. So if you have a working condition at resonance, you should have a damper. That is one of the solutions. Okay, and the reason, as you can see at resonance, what we have is a parallelogram, that it is a rectangular shape, that vector forces, vector representation of the forces form a parallelogram. So the one opposing applied force, if not, is the damper force. And if you have no damper, then you have a problem. So to control, if not, it means you can increase the value of C. Okay, so at resonance, it means that omega over omega n equal to 1, and you can substitute in the amplitude ratio to find what is X at resonance. Okay, so this is resonance amplitude, or you can just call it X resonance, equal to F naught over C omega n. And this is obtained by substituting in this equation, or even the equation before this. Okay, so if you do when omega equal to omega n, it means that this term will be 0. And then you will have X equal to F naught over C omega. Okay, and this will reduce to, okay, so let me just take this on one side. Okay, so at resonance, we will have xk over F naught equal to 1 over square root of C omega squared. So we take it outside the square root, becomes 1 over C omega. Okay, and x equal to F naught, and omega is omega. Okay, should be like that, right? Yeah. Okay, and X resonance become F naught over C omega n. There is K here. Okay, the amplitude is F naught over C omega n. K is equal to, okay, let me make sure. Okay, that is only X, not the amplitude ratio. Okay, so that is X equal to F naught over C omega n all square becomes F naught over C omega n, and this becomes X equal to F naught over C omega n. Or if you use the amplitude ratio, it is xk. At resonance, this becomes 0. And omega over omega n is 1. then xk over f naught becomes 1 over 2 zeta. Okay, and the x resonance becomes f naught over 2 zeta k. Okay, that's substituting in the equation at omega equal to omega. So as you can see from this equation, x at resonance is equal to f naught over c omega n, or f naught over 2 zeta k. So if the value of c is 0, you are dividing by 0, or zeta equal to 0, you are dividing by 0, which means it will go to infinity. Okay, and that's very dangerous to have undamped system working at resonance. Okay, then we talked about the total solution, which consists of homogeneous and particular. And this is the case for zeta less than 1, underdamped. This is the particular solution, and this is the homogeneous solution. Where x1 and phi1 are unknowns to be found from initial conditions on X. If you have underdamped system or damped in general, the plot of the total solution is the summation of is the transient. This is called homogeneous, and this is the particular, and this is the total. So when you add the two, you get the total. The plot of the homogeneous alone is decaying with time. It will vanish. It becomes 0 after some times. The particular solution is a sine wave, so its amplitude is not changing. It's the same. So when you add the two together to get the total solution, there will be distortion of sine wave because you are adding two waves. This becomes a complex wave here. And then become sine wave because the transient will be 0 after some time. This t or tau is any time. And this is why the the particular solution is called the steady state, and a homogeneous solution is called a transient, not which means it's dying out after some times. Okay, this is the note here. It can be seen that xh dies out and x of t becomes x of p only. X of t becomes xp of t only after some time. And this is why the particular solution is very important. So even, and this is only in the starting up of any machine, it will have, shaking vibration because amplitude is higher here than if it is only steady state. Okay, and this is why when we start up our engines or cars, the engine will shake for a short time and then it becomes smooth, or any machine. During the startup, it will have this shaking and then it will become, it will run smoothly. Okay, that is the homogeneous, it's called a transient, and the particular is called a steady state. The part of the motion that dies out due to damping, which is the free vibration part, is called transient, which is temporary. Okay, now we'll have an example of underdamped system. Okay, find the total response of a single degree of freedom or system with M equal to 10 kilograms, C equal to 20 Newton second per meter, K equal to 4,000 Newton per meter. X at 0 this is the initial condition, initial displacement 0.01 meter, and x0 dot equal to 0, which is the initial velocity. So it is a spring mass system with m equal to 10, c 20 Newton second per meter, and k is 4,000 Newton per meter. The question is to find the total solution, the total response or total solution. In vibration, the solution is called response. The response, which means the effect of applying the force and initial conditions. Under the following condition, there are two conditions, or the question to be solved for two conditions. The first one is an external force F of t equal F naught cosine omega t, which is harmonic force, act on the system with F naught equal to 100 Newton and omega equal to 10 radian per second. And the case B, condition B, the free vibration with F of t equal to 0. So in the model we have here is spring mass system with damper. So this is M, K, C, and there is a force applied F of t. And this is part A, when F of t equal to F naught cosine omega t. And this is part A. Part B, when there is no force, the free vibration. Here we have x at 0 is 0.01 and x0 dot equal to 0. A system or part or condition B is the same system but without force, K, C, and M, and that F of t is 0. We have only initial conditions, x at 0 equal to 0.01 and x0 dot equal to 0. In each case, the question is to find the response. Total response is required. The total response is x of t equal to xh of t plus x particular. X of t, as we said, depends on the value of zeta. And xp has to follow the right-hand side of the equation, which is the force. The force is if not cosine omega t, then xp is going to equal to x cosine, not sine, cosine omega t minus phi. Okay, so why we use cosine? Because we have the force is applied, the force applied is a cosine. Okay, this is for part A. Part B, the total solution is only one solution, or total response is x of t equal to xh of t only. There is no particular solution. And again, this depends on zeta, and zeta is the same because this is the same system. Okay, so this is what we will do. In order to find the homogeneous solution, we need to find how much is zeta. So we start with omega n. This is a spring mass system. Omega n square root of k over m is 4,000. Square root of 4,000 over 10 equal to 20 radian per second. Statical deflection, if not over k, is 100 over 4,000 equal to 0.025 meter. Zeta is defined as C over CC. C over CC is defined as 2 square root of k over m. This is one of the expression of CC. Then becomes 20 over 2 square root of 4,000 times 10 equal to 0.05, which is less than 1, under down. Okay, so you can proceed to find omega d because this is under down, and this is valid for under down. omega d equals square root of 1 minus zeta square omega n. Square root of 1 minus 0.05 square multiplied by 20 becomes 19.975. Okay, you can truncate to 2 decimal places, 3 decimal places. And omega over omega n, this is the frequency ratio. We would need this in finding capital X. Becomes 10 over 20. Omega is given, it's 10, given. Part of the question in part A. And omega n is calculated as a 20, so 10 over 20 is 0.5. So this is less than resonance, below resonance. Okay, then x equal to f naught over k. And now this is similar to the equation, but it's introducing that we use here f naught over k and r is omega over omega n. So this is just to make it shorter. Okay, so delta is statical deflection is 0.025 divided by 1 minus 0.05 square or square plus 2 times 0.5 times 0.5 squared. All under square root becomes, the answer is 0.03326 meter. This is the amplitude of the steady state. Okay, the phase is 2 zeta omega over omega n, which is r here, and divided by 1 minus omega over omega n, which is r squared. And substituting, we get the phase equal to 3.8 degrees. But when you substitute in the equation, you should use radian. Okay, so this is the complete solution of the steady steady state. So x particular becomes x cosine omega t minus, I think he's using minus, okay? minus 5. So this equal to 0.03326 cosine omega t, omega is 10t minus 3.8, but this should be in radian. Okay, we'll keep it 3.8, 14.075 degrees, but we know that when you try to calculate the response, you make this all in radian. This should be converted to radian. Okay, this is in radian. Okay, and this is in degrees, so we cannot subtract them. We cannot add two different things of different units. So we either convert the radian or convert the degrees. Okay, for since zeta is less than 1, the homogeneous solution is xh. Okay, maybe we can do it up. Okay, since we found zeta is less than 1, then the homogeneous solution, one of the solution is given by x0, x e to power minus zeta omega nt. You can use cosine or sine omega dt minus phi 0. Okay. You know, if you use sine here, you can use sine, but then phi will have different value. But it is not wrong, it is correct. But I'm just following the question. You can use cosine or you can use sine. Okay, what is x0, phi 0? You don't find them from initial conditions at this stage. Okay, this x0 and phi0 are to be found from total solution. Okay, so the total solution will consist of x equal to xh plus xp, which is shown here with the constants, with the unknowns. x0 e minus zeta omega nt cosine omega dt minus phi 0 plus x cosine omega t minus phi. Now you apply initial conditions. Initial conditions, okay, let's go step by step because those are nonlinear equations, but there are some tricks you can use to find the coefficients, x0 and phi 0. Okay, so we have the first initial condition is x at 0 is equal to 0.01. So it is 0.01, x at 0, x0, e to power 0 is 1, cosine of minus phi is, it is even. Cosine, you know, when you put t equal to 0 here, this will be 0, and this will be cosine of minus phi 0. And the cosine is even. Cosine of minus phi 0, this becomes cosine of phi 0. Cosine is even function. Okay, so this is why in the first term is only x0 cosine phi 0 plus x cosine of minus phi again. This x and phi are known. This is the particular solution is completely defined. So we can substitute for x, which is this is 0.03326, cosine of minus phi. Again, it becomes cosine of phi because this is even. And phi here is in degrees. Now you can use the calculator in degrees, no problem, because this will be cosine of 3.18 or 3.814075. Okay, which is equal to 0.99. It's almost 0, right? Very close to 0. This is why it is very close to 1. Okay, this is one equation. From this equation, the x0 cosine phi 0 can be put on one side. Okay, so this is why we have here x0 cosine phi 0 equal to minus 0.023186. This is one equation, equation number 1. The second equation is obtained by using the initial condition x dot at 0 equal to 0. So it means you have to differentiate this equation here, differentiate x to get x dot, and then substitute for at t equal to 0, and the initial velocity is 0. Okay, you know that for this is to get x dot, we have a product of two functions in this first term. So the derivative of the exponential function multiplied by cosine plus the derivative of cosine multiplied by the exponential function, because those are product. Okay, and then substitute directly. So it is minus 0.05 times 20, so this is zeta times omega n, and e to power 0 is 1, x0 cosine phi 0 plus x0 omega d, which is 19.97 sine phi 0. Okay, sine, you will have sine of minus phi 0 is equal to minus sine of phi 0, because this is odd function. Sine is odd function. So you can try to solve it yourself. You will see there is sine minus phi 0, which should be, you can be replaced by minus sine phi 0. Okay, plus 0.03326 omega after we take the derivative, the system, sine 3.814 degrees. X0 cosine phi 0 can be obtained or used from equation number 1, and then we will have, we can put x0 sine phi 0 on one side. Okay, and this is what we get. This is equation 2. X0 sine phi 0 equal to minus 0.002268. Okay, so those two equations, if squared, you square equation 1 and you add it to the square of equation 2, you will get x0 square common, and this will be cosine square phi 0 plus sine square phi 0, which is 1. This is on the left-hand side. Plus minus 0.023186 squared. The whole thing is squared. Plus minus 0.002268 squared. And then this is equal to 1. You can get x0 from here. Okay, so x0 is the square root of this, because this is equal to 1, and then you can get x0 from here. So this is the first step this is the first constant is obtained this way. To get the phase, or to get phi 0, you can divide equation 2 by equation 1. To get tan phi 0. And then you get phi 0. So the total solution is now complete. Okay, here, which is this one. You just put the values now. The value of x0, value of phi 0, value of x, value of phi, omega, omega d, zeta, and omega n, and becomes a function of time. Okay, so the final solution is x of t equal to x at 0, which is 0.023297 e to power minus zeta omega n. Okay, which is we have zeta is 0.05 multiplied by omega n20, which is 1 times t. So e to power minus t cosine omega d t, which is 19.9 19.9748. Okay, 984 t minus phi 0, which is 5.586765 degrees. Again, this is a radian. You just make sure when you substitute for value of t to make the correct conversion. This is in degrees. So you need to convert. Okay, this is the homogeneous solution plus the particular solution, which is 0.03326 cosine 10t minus 3.814075 in degrees. Again, this is in radian. You can keep it, and this is in degrees to convert to radian. So this is the total solution. And then you can evaluate, as you can see, there is only t here. It's function of time. So you can evaluate or plot x of t for all time. Or just in the exam, it will be fine at a specific time. Okay, for the free vibration, that there is only homogeneous solution. So what we did here is applicable, or we can use all this, omega n z, and we don't need this, zeta and omega d to get the total, to get the homogeneous solution. So it is x0 e to power minus zeta omega nt cosine omega dt minus phi 0. But x0, phi 0 are not same as and obtained in part A. Okay, so those are to be found again using the initial conditions. X at 0 is 0.01 and X dot at 0 is 0. Okay, so applying again those initial conditions, I will not go through details. You get phi 0 is minus 2.8 and you get x0 is 0.01. Okay, so the note, as you can see here, that note that the constant x0 and phi 0 in cases A and B are very different. And this is just to emphasize that you can use the homogeneous solution as we did in chapter 2, but without evaluating the constants from the homogeneous solution. So you take the homogeneous solution with the unknown constants, with the unknown coefficients. Okay, and then you find from the total solution. Okay, so this is what we did in this is a continuation of lecture 2. I will talk about in details of the undamped system when the zeta equal to 0 or when C equal to 0 under harmonic excitation. So the system here is spring mass system subjected to a harmonic force f of t equal to f0 cosine omega t or sine omega t. Both are harmonic. And what you need to find is how much is x and what is the amplitude of x. So you can use the solution we have before, or you can make the derivation from beginning. Okay, so the differential equation for this system, you put C equal to 0 becomes mx double dot plus kx equal to f naught cosine omega t. Okay, which is the same as what we did, but you put C equal to 0. The total solution becomes homogeneous as before, plus particular. The homogeneous solution is C1 cosine omega nt plus C2 sine omega nt, which is what we did in chapter 2. This is the homogeneous, but you don't find x1, C1 and C2, just you make them unknown. Okay, we call them A and B before, but they are constants, so A and B or C1 and C2. So here is XH, homogeneous, plus the particular solution. The particular solution is X, same as before, there is no changes, X cosine omega t minus phi. Okay, X has, if you go back to lecture 2, it is X equal to f naught over square root of k minus m omega square all squared plus c omega squared. So we have c is 0 here. Okay, this is x. So for c equal to 0, that x becomes f naught divided by square root of k minus m omega square all squared. We take this outside the square root, becomes f naught over k minus m omega squared. So when you reach to this stage, you take this outside the square root because this can be minus, right? But minus and square becomes always positive, so you have to take this outside the square root. So it is f naught over k minus m omega squared, as you can see here. So this is x. The phase is phi equal to tan inverse c, I think omega over k minus m omega squared. So for when c equal to 0, this is tan inverse of 0, which is 0. And this is why it is only cosine phi, cosine omega t. So the total solution now is this. Homogeneous, which has the two constants to be found from initial conditions after from the total solution, of course, plus the particular solution if not over k minus m omega squared cosine omega t. So everything is known here in the particular solution. And omega, of course, is known because omega is square root of k over m. So we don't have to write this equation again. So we need to find C1 and C2. So using initial conditions to find C1 and C2. Okay, just I will finish this page and then you can leave. So x at 0 is x0. X dot at 0 is x dot x0 dot, which is it means they are given. Just they are put as parameters, but they are given. So when you substitute in the total solution, you will get C1 equal to x0 minus f naught over k minus m omega square, and C2 is x0 dot over omega n. And you can substitute to get x at t equal to x0 minus f naught over k minus m omega square cosine omega n t plus x0 dot over omega n sine omega n t, and so on, plus f naught over k minus m omega square cosine omega t. And we will for the particular okay, this is the next page. Okay, up to here. So next time we will talk about how to plot and also we will look at the particular solution in details. Okay, we'll see you inshallah next week. On Sunday, those who are absent, you were absent, they can do the makeup. Those who want to repeat, they are welcome. But the way I will mark their papers will be different because they have the second chance. Yeah, بالتوفيق.